So our next speaker is Yoshiki Hatta. He's a postdoctoral researcher at NAOJ, and research interests include asteroseismology, stellar evolution, and inversions. And today he's going to talk about asteroseismology of a possible Roku straggler.
A long time, and today I'm going to talk about astroseismic studies of one of the Kepler targets. So first of all, let me explain what is this star. This star is one of the Kepler targets, so done by Kepler for 4 years. And according to the Kepler input catalog, it's categorized as a main sequence A-type star. And here is a schematic view of the interior of a typical main sequence A-type star. Usually they have a convective core and broad radiated region, and also the thin, very thin outermost convective envelope. This is very typical structures, internal structures for A-type star. And then for astroseismic properties of the star, P modes, G modes, and mixed modes are detected for the star. And here, P mode is a mode whose restoring force is pressure. And for G modes, the restoring force is gravity. And mixed modes are actually having the mixed nature of P modes and G modes. And here is an amplitude spectrum of the star obtained by Fourier transforming the Kepler light curve. And it is clearly seen that in low frequency region, there are many G mode peaks. And in high frequency region, we see P mode peaks very clearly. And the important thing is that using these modes, we can probe both the deep radiated region and the envelope, because this is because it is well known that P modes are mainly established in the envelope, like this. So we can probe the envelope structure, we can probe envelope region using P modes. And in contrast, G modes are mainly established in the deep radiated region around there. So we can infer the deep radiated region structure using G modes. So roughly speaking, in the case of this star, we can probe almost the whole interior. This is a very nice property in the case of this star. And another good point is that this star is exhibiting well-resolved frequency splitting for both P and G modes. And actually, this feature is very rare. There are only 3 main sequence stars which exhibit well-resolved frequency splitting for both modes, even in Kepler input catalog. And here are examples of frequency splitting. We see the modes are clearly well separated. And thanks to this very nice property, there have been a number of astroseismic studies about the star, including astroseismic modeling and inferring internal rotation of the star, and also even the asphericity of the star has been measured based on the observation of this well-separated, well-resolved frequency splitting. And then let me explain the first astroseismic study of the star, Kurtz et al. 2014. Their first aim was to obtain a reference model for rotation inversion based on grid-based modeling. And here are 2 main results about the best model they obtained. And actually, they are very interesting. The first result is that the initial helium abundance of the star is very large, and which is too large compared with ordinary initial helium abundance, about 0.26. And another result is that their model cannot reproduce the observed P mode frequencies well. So there should be something wrong with the envelope of the model. This is because usually P mode frequencies are determined by the envelope structures. So based on these 2 results, are suggesting the possibility that this star may well have gained helium from the outside. But anyway, they based on the model, they infer the internal rotation of the star, which is the second aim in their paper. And to do that, they carry out rotation inversion, and they use the model with the high initial helium abundance model as a reference model to carry out inversion. And they obtain these two results. And the first result is, again, very important. And they found that this star is rotating almost rigidly throughout the star. This result leads to the current understanding of stellar internal rotation. Actually, after Kurtz et al. 2014, there have been a number of astroseismic inferences on internal rotation of main segment stars, but the results are more or less all the same. So almost all the main segment star is rotating almost rigidly throughout the star. So this is the current view about stellar internal rotation obtained by the astroseismology. And the second result was again an unexpected one for them, that the envelope is rotating slightly faster than the deep radiative region. And the simplest explanation could be, again, the star might have gained angular momentum from the outside to realize this rotational profile. So combined with the these results obtained based on stellar modeling, and this result too, it is suggested that this star has experienced some events resulting in helium enhancements in the envelope during the evolution, and became a blue straggler star. And blue straggler stars are stars that are left on the main segments above the turnoff point like this. Here is a color magnitude diagram on the globular cluster M3. And usually in a globular cluster, the more massive a star is, the earlier the star leaves from the main segments. But some of them are still on the main sequence. They are called blue straggler stars. And the origin is thought to be interactions with other stars, such as stellar merger or mass accretion. And previously low mass progenitors experienced stellar merger or mass accretion and then gained the mass, and now it is on this main sequence. This is how this is the formation channel for blue straggler star. And because PIC 1114512 could be such kind of strange star or blue straggler star, Takada Hidai et al. 2017 measured the surface abundance of the star to know the star more based on spectroscopy. And their main result is that the abundance pattern of the star is similar to that of a typical blue straggler star, concluding this star is probably a blue straggler star. So now it looks more probable that the star may well have experienced some interactions with other stars. Here, there's room for improvements since there has been no attempt to model the star in a non-standard manner, taking effects of helium enhancements in the envelope into account. So the first goal of this study is to construct a non-standard model reproducing the observed frequencies based on these assumptions that the star was born with an ordinary initial helium abundance. And then the envelope of the star has been somehow modified by some events during the evolution, and the helium enhancements happened. This is the first goal. And another point is relating to internal rotation of the star. Hatta et al. 2019 inferred the two-dimensional internal rotation of the star based on the previous high initial helium abundance model. And they have confirmed the Kurtz et al.'s result, and they have also found the latitudinal dependence of the internal rotation for the star. Actually, the final result is very interesting. They found a hint for the fast convective core rotation. And this is interesting because this result especially differs from the current view, as I said, that most of the main segment stars are rotating almost rigidly. So if this is true, or if this is confirmed, this is very interesting result. But here is an issue. There is that model dependence matters in rotation inversion. So this is the second goal. We have the second goal, though more minor compared with the first one. But the second one is to infer the internal rotation again based on the non-standard model of the star. And it's significant because if the fast convective core rotation is confirmed again, it may pose a challenge to the theory of angular momentum transfer inside the stars. So here are three topics in this talk. First one is non-standard modeling of the star. And then based on the model, I carry out rotation inversion, and I'm going to show the results. And finally, I'm also going to discuss a possible relation between the inferred structure and dynamics inside the star. So let me start the first part. Here is our strategy, consistent of two steps. In the first step, we construct core models based on the observed high-order G-mode period spacing pattern, and starting with ordinary initial helium abundance. This is a very important point. And secondly, we artificially modify the envelopes of the core models by increasing helium abundance there to reproduce the observed P-mode frequencies. So here in this step 2, we mimic envelope modifications caused by some events. And then moving on to explain in more detail. And in the step 1, we especially focus on the so-called G-mode period spacing, or delta PG. And this is one of the most important astroseismic parameters, which enable us to probe deep interiors of the star. And asymptotic theory of stellar non-radial oscillation tells us that the high-order G-mode period spacing is constant. And here, delta PG is defined as the difference between the G-mode period with consecutive radial orders. And this is the expression for theoretical expression for delta PG. And L is spherical degree. And actually, delta PG is inversely proportional to the integral of Brown-Weiss frequency. You see. And important point is that the Brown-Weiss frequency varies as the star evolves. So accordingly, delta PG, the value of delta PG can also change as the star evolves. So that's why observed delta PG can be used as an indicator for stellar age or sometimes mixing processes. And here is an amplitude spectrum of the star again. And when we zoom in this G-mode frequency region, we see the fine structures like this, and we can determine the delta PG, the value of delta PG observationally by subtracting the periods between these consecutive radial orders. Okay. And then here is a comparison between the observed delta PG and modeled numerically calculated delta PGs. And here models are expressed with black curves and blue curves, and the observation is represented by red squares here. And horizontal axis is G-mode period, and the vertical axis is delta PG. So I'm going to explain how they calculated the numerical computed delta PG pattern. So first, they prepared the stellar model and they decided the stellar mass and initial chemical composition, and they started the evolution with ordinary one-dimensional stellar evolution course, and they stopped the calculation when the central hydrogen abundance reaches 0.549. And for this model, they calculated the eigenfrequencies for G modes and taking the subtraction between neighboring G modes, they can plot this delta PG pattern for certain model. And then they continue the evolution until the central hydrogen abundance reaches 0.208 and do the same thing and plot the delta PG and so on and so on. And here we clearly see that as a whole, delta PG, or especially the mean value of delta PG, decreases as the star evolves. And what Kurtz et al. Did is to fit the mean value of the observed delta PG pattern, here represented by those dotted line, with the numerical computing delta PG pattern. And finally, they found that this star is at the terminal edge main sequence stars, meaning that this star has exhausted almost all the hydrogen and the nuclear core. This is what they did by focusing on delta PG. In this study, we tried to do more. And so here's a point. We clearly see some statistically significant deviations of the observed delta PG pattern from a constant value. Actually, the observational uncertainties are very small. The B cannot see in this plot. So these deviations from the mean value is statistically significant. And it is known that different treatments in mixing processes in the stellar evolution calculation have impacts on delta PG patterns. So we further attempt to reproduce this observed pattern as well as possible by training a parameter for especially overshooting. And why do we focus on overshooting? Because it certainly affects the delta PG patterns. And here is a comparison of observed delta PG pattern with red curves, and other delta PG patterns are computed based on some stellar models with different treatments, different strength of overshooting. And here we adapt the formulation of Harwick 2000 to describe overshooting. And as you see, as we change the extent of overshoot, the numerical computed delta PG pattern changes. And in this case, so this green case is most appropriate to reproduce the observed delta PG pattern compared with other cases. So this is what we do in the first step, and we discuss delta PG pattern later more. And then here is a specific parameter range for grid-based modeling. In the step one, we use MESA, ordinary one-dimensional stellar evolution code, and here's a parameter range. We adapt typical values for main sequence A-type star. Here the important thing is that we set initial helium abundance to be relatively low compared with the previous studies. And we exclude high initial helium abundances from the parameter range because we would like to test the scenario of non-single star evolution. And for each set of mass and initial chemical compositions, we determine a model which reproduces the observed delta PG pattern best and call it a core model. Okay, that is the procedures in the step one. And then we are going to fit observed p-mode frequencies by changing or modifying the envelope of the core model, which constructed in the step 1. And to do that, we have developed some schemes to modify chemical compositions in the envelope of a certain stellar model based on the formulation of linear adiabatic oscillation. And here is a schematic diagram for the scheme. And here is a model obtained in the step 1. So this is a core model. And we perturb the chemical composition in just the outermost layers, like this. And we fix the core region because we already fitted G-mode frequencies or G-mode period spacing patterns. So we didn't modify the core region. We just perturb outer region. And because of this calculation, this model is not in hydrostatic equilibrium anymore. And it must oscillating around some equilibrium point. And by assuming a adiabatic process, we can determine this new equilibrium point. And we adapt this new equilibrium point as a new model. And this is the main part in the step 2. And actually, though this new model is in the hydrostatic equilibrium states, it can deviate from thermal equilibrium. So we lastly resettle to the thermal equilibrium states via MESA by just evolving this new model for the corresponding thermal time scale. And here are examples of modified envelopes. Envelopes, yes. And here I plot the hydrogen profiles from the center to the surface of the star. And here the horizontal axis is in units of solar radius. And black one is unperturbed one. And as I said, in the inner region, we didn't modify the chemical compositions because G-mode frequency is already fitted. And to describe envelope modification, we prepared 2 parameters, and one is the extent, which is how we modify the envelope. And another parameter is depth, which determines how deep we modify the envelope. So in this case, the depth is the same, but there are 4 ways of 4 different extents. And basically, the more helium increases, so from purple to red in the envelope, the more P or mixed mode frequencies get higher. And then we look for models reproducing the observed frequencies, gradually changing the 2 parameters, depth and extent. This is what we did in the step 2. And here are frequencies of the envelope modified model compared with the previous model. And here modeled frequencies are represented with solid lines, and observed frequencies are represented by dashed lines. And here's Kurtz et al.'s model, and here's our non-standard model. And as we see, observed frequencies are reproduced as well as in the previous model. But to be honest, there's no big improvements in terms of how well we fit the observed p-mode frequencies. But the most important point is that in the previous model, or when we assume a single star evolution for the star, we need to accept this high initial helium abundance to explain these observed frequencies. But in a non-standard scheme, we do not have to assume such high initial helium abundance. And by starting with relatively ordinary initial helium abundance, we can explain the observed p-mode frequencies. So that is definitely improvement, an improvement. So then I'm going to discuss a little bit whether this star has experienced single star evolution or not. And in terms of abundance pattern, as I said, this star, the abundance pattern of this star is similar to those of typical blue star clusters. And another point is that for this star, no nitrogen enhancement, no carbon depletion has been measured according to Takada Hidai et al. And these features are very important because for some, in some globular clusters, there are very peculiar single stars with high initial helium abundance, about 0.3 or larger, and all of them are exhibiting this property. So in the case of KIC 1114512, there's no nitrogen enhancement, no carbon depletion. So this star is not such a peculiar single stars. So then in terms of stellar models, we can, in this study, successfully construct a non-standard model of the star to explain the frequencies. So combining with these points in view, we are now considering that the star might have experienced non-single star evolution during the evolution. So then I'm going to talk about internal rotation of the star, focusing on the convective co-rotation based on, focusing on the convective co-rotation. And here I show again the rotational splitting based on which we infer stellar internal rotation. So here are examples of rotational splitting for the star. This is the case of area equal 1 mode. So there are m equal -1 to -1 multiplets. And this panel shows the case of area equal 2. So from we see m equal -2 component and m equal to 2 m equal 2 component. And so we can, so important point is that the amount of frequency shifts here represented by di for some mode is relating to internal rotation in this equation. And here ki is the so-called splitting kernel, which can be computed once we obtain a reference model. And in this study, we use the non-standard model as a reference model. And the number of this linear integral equation is the same, identical to the number of the observed rotational shifts. And by inverting the set of linear integral equations, we can finally infer internal rotation profile. And actually, the number of modes, the observed modes, is very small compared with, for example, the case in helioseismology here. But we can infer internal rotation profile. Oh, sorry, maybe I will skip these parts. Oh yeah, here. And next, I'm going to show you how to carry out inversion, but I'm not going to explain it in detail. So here, just Thereson modeling on the rotational profile. And here, we divide the stellar interiors into 3 sections. And we assume that each section is rotating rigidly. Okay, so with the rotation rates omega-1 and omega-2 and omega-3 respectively. And then based on this assumption, we can rewrite the equation we saw in the last slide like this. And finally, we obtain the matrix equation. And here E is the observational uncertainties. And it is relatively easy to invert the final line to estimate omega j, because now what we have to estimate, the number of what we have to estimate is just 3. And here is a result of the Threeson modeling based on the previous high initial helium abundance model. And this is already reported in Hatta et al. 2019. And as we see in the radiative region, the rotation rate omega 2 and omega 3 are almost the same, so rotating rigidly. But when we see the convecting core rotation, we see that the convecting core is rotating around 5 to 6 times faster than the other region. This is what I said in the introduction. And then, sorry, I skipped this part. These are not related part are here. And then I carried out Threeson modeling based on the envelope modified model. This is a new part. And actually, the results are almost unchanged. For omega 2 and omega 3, they have almost the same rotation rates. And when we see the convecting core, it is rotating now around 10 times faster than the other regions on the star. So we were very relieved to know that this inference on fast convecting core rotation is unchanged even when we use the different newer model of the star. And here's a summary slide for rotational profile on KIC 11145123 because we have carried out some other inversion techniques like OLA in two-dimensional array. So, but as in short, the radiative region is rotating rigidly, but there's definitely a differential rotation, both in radial direction, so here, and also in the latitudinal direction. And we also found the convecting core is rotating very fast. And this fast convecting core rotation has been also inferred by the Bayesian rotation inversion recently developed by us, and it's submitted. But now we have very severe comments from the referee, so maybe we have to reanalyze the part. But yeah, we can confirm the part with a different scheme. So finally, I'm going to discuss internal dynamics of the star, focusing on a possible relation between the chemical composition gradient and the rotational velocity share. And key parameter is delta PG pattern again. And here is a comparison of observed delta PG pattern in black and modeled delta PG pattern in red. And this red one is obtained based on the non-standard model we constructed. And as we see, the general trend is partly reproduced by tuning the extent of overshooting. But the shorter periodic component is not. So is there any room for improvements? So that was what we were discussing. And actually, the answer is yes. And because it is theoretically known that oscillatory components in delta PG patterns are thought to be caused by sharp features in Brown-Weiss frequency. And it's also known that there are two important quantities determining the oscillation in delta PG patterns. And one is the strength of the sharp features. And another is position in the sharp features in Brown-Weiss frequency. And for example, Miglio et al. Provides us with the explicit form for the oscillatory component in delta PG pattern like this, with this sinusoidal component. And this A star is related to the strength of the sharp features. And as we see, this strength, as this strength becomes larger, the amplitude of the oscillator component becomes larger. And as we change the position in the sharp features, the period of the delta PG pattern also changes. And please note that here, the pi r, the variance radius, is defined as like this. So the integration of Brown-Weiss frequency. And pi 0 is the variance radius for the whole G-mode cavity. And pi mu is defined like this. So the variance radius of the position of the sharp feature. So according to this expression, the periodic component in delta PG pattern for one cycle is giving us the inverse of the ratio between pi 0 and pi mu. Okay. And then what we would like to do is to make the shorter periodic component have a larger amplitude. So following this expression, what we have to do, or what we need is to have a sharp feature in Brown-Weiss frequency. Here's the Brown-Weiss frequency inside the model. Around this value is close to 3, because we would like the short periodic component with 3 appear. Okay, and here is the Brown-Weiss frequency, and here is the hydrogen abundance profile for the model. So actually, we can artificially make the chemical composition gradient steeper around that region by using the scheme that we have used in non-standard modeling, because the scheme enables us to compute a stellar model whose chemical compositions are arbitrarily modified. And here I show the hydrogen profile, and I gradually make the hydrogen abundance chemical composition gradient steeper here. And correspondingly, Brown-Weiss frequency has much sharper feature from blue to red here. And finally, the corresponding delta PG patterns numerically computed based on these pattern models like this. And as we see, from blue, green to red, the amplitude of the delta PG pattern becomes larger and larger. So the shorter periodic components appears as we expected. Because this is artificial test, the next question should be what realizes the steeper chemical composition gradient around here in reality. And maybe there should be some possibilities, but now we are considering one possible resolution that is much bigger elemental diffusion. And because we would like to keep the chemical composition gradients not smoothened, so that's why we consider much bigger elemental diffusion. And here comparisons of ordinary diffusion model represented by red, and much bigger diffusion model represented by blue. And as we see, the chemical composition gradient is much steeper in the case of blue line compared with the red one. And so is the Brown-Weiss frequency. And finally, when we computed the delta PG pattern based on the weaker diffusion model, it has larger amplitude compared with the ordinary diffusion model. So now we are thinking that weakening the elemental diffusion processes in stellar evolutionary state in the evolutionary computations works. And here I'm going to discuss possible relation between the infrared fast core rotation and weak diffusion based on the rotation inversion we have a hint for fast convecting core rotation. And because the radiative region is rotating much slower than the convective core, there should be a strong velocity share. And on the other hand, we are based on the analysis of delta PG pattern, we have found that the chemical composition should be much steeper in the deep radiative region, suggesting much weaker elemental diffusion. And now, is there any relation between them? And one possible relation is the rotational velocity share causes instabilities, leading to extra mixings there, and somehow counteracting the elemental diffusion, and which finally results in steeper chemical composition gradients. And this scenario is attractive because it somehow resembles what is happening on the solar Takoku line. Actually, that chance is small because actually rotational shear instability mixing can make the chemical composition gradient steeper locally, but such a sharper feature should be so close to the convecting boundary that the buoyancy radius is too small to reproduce the short periodic component. So if the rotational shear instability occur, this is so close to the convecting core, and the buoyancy radius of the sharper feature is not large enough. And we can confirm that by, again, computing the perturbed models like this based on the scheme. Yeah, and here I show you the hydrogen abundance profile. And from blue to red, gradually broadening the region, mixed region, mixed by rotationally induced mixing. And actually, as we expected, the chemical composition has become partly steeper, although other mixing region is uniform. But because this sharp feature, well, the buoyancy radius of this sharp feature is too small, we do not see any short periodic component in delta PG pattern. Although this is as we expected, this is, yeah, but this is as we expected. So based on these computations, now we are thinking that the much weaker diffusion is not relating to the shear instability mixing. So the diffusion process should be really much weaker compared with the ordinary one-dimensional stellar evolution calculations. So here are conclusions in this study. So the main conclusion is that we can explain the observed frequencies based on the assumption that KIC 1114512 is a blue straggler star. And we have also obtained following suggestions. The first one is the convecting core of the star is rotating much faster than the other regions. And the second one is the chemical composition gradient just outside the core of the star is much steeper than that in the current models. So, so I think this is almost our last slide, and here here are future prospects about delta PG patterns and internal rotation. And I think analyzing delta PG patterns is very promising because now delta PG patterns have been on for many Kepler targets, and there have been a number of researches focusing on delta PG pattern and mixing processes such as overshooting, elemental diffusion, and so on. But I think there's no such study focusing on rotational induced mixing and delta PG pattern. So I think this is a very promising and interesting topic in the near future. And in terms of internal rotation, the number of astroseismic studies on stellar internal rotation has been increasing, but now it is very difficult, as you know, it is very difficult to explain the observation based on some numerical calculations of angular momentum transfer and so on. So because I'm not an expert in numerical simulation, but maybe we need more theoretical works. And also and another approach might be we need more observational constraints for internal rotation. And in that point, ensemble inversion can be useful, which Hannah, Suijin, and I are working on in this project. So please, and maybe Suijin is going to talk this ensemble inversion next Friday. So please enjoy that talk. So here's just a summary of my talk. So that's it. Thank you. Thank you for listening.